We're talking about the vacuum. Yep, the profound power of nothing. You see, for almost 2,000 years, this one powerful phrase from Aristotle was basically scientific law. I mean, this is one of history's greatest thinkers, right? He argued that empty space was just physically impossible. Nature, he said, hates a vacuum. Any empty space would just get instantly filled up by whatever's around it. So true emptiness, nope, couldn't happen. But, Aristotle's view wasn't the only game in town. Before him, you had Democritus, who had this totally different idea. A universe made of just two things, tiny little atoms, and the empty space, the void, that they move around in. So yeah, the ancient Greeks were seriously divided on this. Could a true nothing even exist? Okay, so this wasn't just some casual philosophical debate, It was a massive roadblock. Because Aristotle's view was so dominant in Western thought, any real physical experiments on empty space, they were basically off the table for centuries. All right, let's talk about the power of nothing and the first real proof. For centuries, this whole thing was just talk, right? Purely philosophical. But then, in the 17th century, the argument finally jumped out of people's heads and into the real world with a super dramatic public experiment. I mean, think about that timeline. After a wait of nearly 2,000 years, this German physicist, who was also a mayor, by the way, named Otto von Guericke, comes along and invents a device that would finally, once and for all, settle this ancient debate. And this is what he built, the world's very first mechanical air pump. It was this machine made of brass cylinders and pistons, and its whole purpose was completely revolutionary. It was designed to physically suck the air out of a sealed container and, for the very first time in history, create a man-made void. And wow, the way he proved it was pure showmanship. He did this brilliant public display where he fit two big copper half-spheres together to make a ball, and then he pumped all the air out. What happened? Well, the pressure from the outside atmosphere slammed them together so tightly that not even two teams of horses could pull them apart. This wasn't just proving a vacuum could exist, it was this incredible demonstration of the immense, invisible force of this ocean of air we're all living in. Okay, so even though a vacuum was now possible, the technology itself had some serious limits. And this created a whole new bottleneck for science that would actually last for another 200 years. So the big question became, how do you create a truly empty space? See, the problem with piston pumps, even the best ones, was that they always had tiny leaks. The mechanical seals just weren't perfect. They can never create the super high-quality vacuums that were needed for really delicate scientific research. So what was the solution? Well, the breakthrough didn't come from a better piston. It came from liquid metal. In 1865, this chemist, Hermann Sprengel, had this totally ingenious idea. The solution wasn't a better machine with tighter seals, no. It was to get rid of the machine parts altogether and use something completely different, falling drops of liquid mercury. And the way this thing worked was just so elegant. Check it out. As each heavy drop of mercury fell through this skinny glass tube, it created a perfect seal. It would trap a tiny little pocket of air from whatever container they were trying to empty, so each drop was basically acting like a flawless liquid piston, carrying the air down and pushing it out the bottom, one little bubble at a time. Now, this was definitely a slow process, but man, was it efficient. The Sprengel pump could create a level of emptiness nobody had ever seen before. It could get the pressure inside a glass jar down to just 1/1,000,000th of the normal atmosphere. That was the highest vacuum in the world at the time, period. All right, now we get to see the invisible. This new, super powerful vacuum pump wasn't just a small improvement. It was like a key that unlocked a door scientists didn't even know existed, and it directly led to what historians now call the second scientific revolution. For the very first time, researchers could shoot electricity through these glass tubes that were almost a perfect vacuum. And when they did, these mysterious, beautiful, glowing beams would appear. They had no idea what they were, so they just called them cathode rays. You see, with all those pesky air molecules finally out of the way, the true nature of reality just started revealing itself, and it happened fast. It was like a cascade of discovery. First, in 1895, X-rays. Then, just a year later, radioactivity. And then, in 1897, the biggest discovery of them all. Okay, so this brings us to the discovery of the electron. All of these incredible discoveries were connected, and it all came to a head in 1897 with a British physicist named J.J. Thomson. He decided to focus on the cathode rays themselves. He just had to solve the mystery. What are these things? So, inside his special high vacuum tube, he zapped the cathode rays with both electric and magnetic fields. And because his vacuum was so good, with almost no air molecules to get in the way, he could measure exactly how the beam bent. His math proved they weren't light waves. No, they were streams of tiny particles. And these particles had a negative charge. But here's the real shocker. They were almost 2,000 times lighter than the smallest known atom, hydrogen. He had discovered the electron. This was the very first subatomic particle ever identified. And it just completely shattered this ancient idea that the atom was the smallest, most fundamental thing in the universe. It turns out atoms were made of even smaller pieces. I mean, think about that. The quest for nothing had revealed the fundamental building block of matter and electricity. It's a straight line, right? Springle's amazing pump gave scientists the perfect vacuum, and from that vacuum came this absolutely monumental discovery. The 2,000-year quest to create nothing literally gave us the particle that makes our entire electronic world possible. How to make a practical electric light. They had the basic idea down, but they kept slamming into a wall made of physics. So here was the core problem. If you try to pass electricity through a thin wire, a filament, in the open air, the oxygen in the air makes it burst into flames and burn out instantly. Poof, it's just a flash, and then it's gone. The whole dream of a long-lasting electric light was completely dead on arrival as long as oxygen was part of the equation. So what do? Well, inventors figured out they had to get the air out. The big idea was to stick the filament inside a glass bulb and then suck out as much of the air as humanly possible, creating a vacuum. And this wasn't just a small change, this was everything. This was the key. And this, right here, was the massive breakthrough. Because of new tech, like this thing called the Sprengel mercury pump, inventors like Edison and Swan could finally pull off the super deep vacuum they needed. And all of a sudden, those fragile little filaments, they didn't burn out, they just glowed. On and on for hundreds of hours. And just like that, the light bulb was born. And with it came a brand new industrial hunger for vacuum technology. But here's where the story gets really interesting. Perfecting the light bulb wasn't the end of the journey. Oh no, it was actually the beginning of a completely different one. And it was all because of an annoying little side effect. So picture this, it's 1883, and Thomas Edison is trying to make his bulbs last even longer. But he's got this frustrating problem. Black soot keeps forming on the inside of the glass. While he's trying to figure out why, he decides to stick an extra metal plate inside the bulb. And that's when he noticed something really, really weird. What he'd stumbled upon totally by accident was a process we now call thermionic emission. It sounds super technical, but the idea is actually pretty simple. When you heat up a piece of metal in a vacuum, its electrons get so much energy that they literally boil off the surface and just fly out into that empty space. That's what was happening inside his light bulb. And look at what he found. When he connected that extra plate to the positive side of the battery, a mysterious current started flowing from the hot filament to the plate, right across the empty vacuum. But then, when he switched the wire to the negative side, nothing. The current just stopped dead. It was like an electrical one-way street, and nobody had a clue why. Now, you have to remember, Edison was a very practical guy. He was all about what sells. So he patented this weird thing. He called it the Edison effect. But since he couldn't think of any way to make money off a one-way current inside a light bulb, he basically just filed the patent away and forgot about it. And for 20 years, one of the most important discoveries of the century just sat on a shelf, collecting dust. So for 2 decades, nothing. But this is where the story takes a fantastic turn. Edison's forgotten little solution was about to meet its perfect problem, and it was going to happen in a totally different area of technology. I mean, this timeline really says it all. 20 years. An entire generation went by while this key to the future just lay dormant. Then, all the way in 1904, a British physicist named John Ambrose Fleming remembered seeing a demonstration of it and had this incredible aha moment. So what was the problem he was trying to solve? Well, Fleming was working for Guglielmo Marconi, the father of radio, and their first radio receivers were, to put it mildly, terrible. They were, as the source here says, erratic, fragile, and insensitive. They just weren't good enough to reliably pick up the super faint radio waves that were traveling through the air. And that's when the light bulb went off for Fleming. No pun intended. He realized that Edison's electrical one-way street was the exact tool he needed. You see, radio waves are an alternating current, AC, flipping back and forth like crazy. Fleming knew that if he could somehow turn that weak, messy AC signal into a steady, one-way direct current, or DC, it would be easy to measure. The Edison effect was the perfect electrical valve for the job. So he built this thing, the oscillation valve. It was just a simple vacuum tube with two parts. And it did one thing perfectly. It used the Edison effect to turn those useless, messy radio waves into a clean, usable DC signal. This little device, the world's very first diode, made reliable radio possible, and really, it marked the official beginning of the electronic age. Okay, so now they could detect a signal, but that was just the start. The next massive leap forward was figuring out how to take a tiny, weak signal and make it powerful. This is where amplification comes in. So, hot on Fleming's heels, just 2 years later, an American inventor named Lee de Forest comes along. He has an idea to improve Fleming's valve. He takes it and adds a third piece inside, a tiny, delicate little wire mesh that he called a grid, and he puts it right in the middle of that stream of electrons. He called his new invention the Audion. Now, the way this worked is just brilliant. The grid acted like a gate, or maybe an even better way to think about it is like a Venetian blind. By applying a tiny, tiny little electrical signal to that grid, you could control the huge flow of electrons streaming past it. A tiny twitch on the grid could open or close this massive electronic floodgate. And the result? Whoa, amplification. A tiny, almost undetectable signal coming in on the grid could be perfectly copied on the other side, but now it was 100 times stronger or even more. You could literally take a whisper and turn it into a roar. This changed everything. I mean, almost overnight. Amplification is what made long-distance phone calls across the country possible. It's what allowed us to start broadcasting the human voice over the radio, not just the static-filled clicks and pops of Morse code. The entire world of telecommunications was just transformed. So you see, this whole chain reaction, from a light bulb to a detector to an amplifier, it didn't just create a few cool gadgets. It gave birth to a whole new industry. And with that came massive legal fights and manufacturing challenges on a scale the world had never seen before. And of course, whenever there's that much money and power on the line, what happens? Lawsuits. Tons of them. The Marconi Company, which had Fleming's patent, sued de Forest, saying his Audion was just a copy. The legal fights got so nasty, and they slowed down progress so much that during World War I, the US government had to literally step in and force everyone to work together just to get the tubes they needed for the war. That legal battle raged all the way to the Supreme Court and wasn't settled until 1943. And on top of all that, there was one final hurdle. The world was now screaming for millions of these new vacuum tubes, but the old mercury pumps they used for light bulbs were agonizingly slow. It could take hours to make a single one. So this created a huge bottleneck, and that forced another wave of innovation, creating high-speed industrial vacuum pumps just to feed the world's new appetite for electronics.
Pumping something usually means pushing it, right? Like water or even the air in your tires. But what happens when the very thing you're trying to pump is so spread out, so sparse, that it just can't be pushed? Well, that's the bizarre challenge that had scientists totally stumped for decades.
Okay, so to get our heads around this riddle, we first need to understand that gas doesn't always play by the rules we think it does. Depending on the pressure, it's like it lives in two completely different worlds. And this slide just lays out those two worlds perfectly. On the left, you've got what's called viscous flow. Just think of a packed concert, shoulder to shoulder, with billions of molecules jammed together. If you push one, they all kind of move together like a fluid. But as you pump more and more of them out, you enter this other world on the right, molecular flow. This is like having maybe 3 blindfolded people wandering around a massive empty gymnasium. They almost never run into each other, they just bounce off the walls totally at random.
It all comes down to this one crucial idea called the mean free path. That's just the average distance a molecule flies before it smacks into another one. Back in that crowded concert, it's almost nothing, fractions of a millimeter. But in the empty gymnasium of a high vacuum, a single molecule could travel the entire length of the room before it ever hits anything else.
And that enormous travel distance changes everything. In molecular flow, the gas loses all its fluid-like properties. You can't push it. You can't suck it out with a normal pump because the molecules are just too far apart to transfer any force to each other. Your standard pump? It's just completely useless.
All right, let's dive into the problem this created and see how one brilliant physicist started to wrap his head around it.
This guy right here is Wolfgang Gade, a German physicist who became obsessed with this problem. His first big idea, back in 1909, was the molecular drag pump. The idea was to use a super fast spinning cylinder to literally smack individual gas molecules and, well, drag them towards an exhaust. It was a really clever idea, right? Using momentum instead of pressure. But it required incredibly precise, tight mechanical parts, which made it super fragile and ridiculously expensive. A great first try, but not practical.
So we're back to the same fundamental challenge. If you can't push them like a crowd and smacking them one by one with a spinning rotor is way too hard, how in the world do you get these lonely pinball-like molecules out of the room?
And this is where Gadiro had his true stroke of genius. He realized he could move the molecules using something almost like a ghost, a high-speed stream of vapor.
So in 1915, he unveiled his masterpiece, the diffusion pump. And this is the most incredible, mind-bending part. It could create an unbelievably high vacuum with absolutely zero moving mechanical parts. I'm serious, nothing. Just elegant physics doing all the work. So how does this magic actually work? Okay, let's walk through it. First, you boil some mercury at the bottom. That creates a really high-speed jet of mercury vapor. This jet shoots up and is directed past these little slits that are connected to the chamber you want to empty. Now, random air molecules just kind of wander into those slits, and bam, they get slammed by these heavy, super-fast mercury atoms. Those collisions knock the air molecules down towards an exhaust pipe. Then the mercury vapor hits the cold outer walls of the pump, condenses back into a liquid, and just drips right back down to be boiled all over again. It's a perfect, silent, continuous cycle.
Now, Gade's invention was absolutely revolutionary, but believe it or not, it was just the beginning. Over the next 15 years, this brilliant concept was about to be perfected into a real industrial powerhouse.
And the pace of innovation was just stunning. Look at this. Gade invents the pump in 1915. Just 1 year later, an American chemist comes along and radically improves it. And then, by the late 20s, a final critical flaw gets solved, and this thing becomes the global standard.
And this is just a perfect example of how science works, with people building on great ideas. Across the Atlantic, a Nobel Prize-winning chemist named Irving Langmuir reads Gade's paper and almost immediately sees a way to basically turbocharge the whole design.
Langmuir realized that Gade's narrow little slits were actually a bottleneck, so he just got rid of them entirely. Instead, he designed this cool umbrella-shaped deflector. It took the vapor that was shooting upwards and blasted it fiercely downwards, creating this wide, powerful cone-shaped curtain of vapor. It was less like Gade's gentle stream and more like a powerful leaf blower, just violently blasting any stray air molecules straight for the exhaust. This one simple change made the pump phenomenally faster.
But there was just one last big problem. Boiling mercury is incredibly toxic. It was super dangerous for the people working with the pumps, and it could even contaminate the very electronics they were trying to build. The solution, which came along in the late 20s, was pure chemical elegance. Specially designed synthetic oils that had an extremely low vapor pressure. They did the exact same job as the mercury, but they were safe, they were stable, and they were efficient. And just like that, the modern diffusion pump was born.
So after all that innovation, what's the ultimate legacy of this clever, part-free invention? Well, it all comes down to two things: speed and incredible scale.
I mean, remember, the whole magic trick here is the lack of moving parts. There are no spinning blades, no tight tolerances you have to worry about. And what that really means is that you can build these things to be absolutely massive.
And the difference in scale is just staggering. A really high-tech mechanical pump, a turbo pump, is limited to an inlet of about 250 millimeters. But a diffusion pump, you can build one with a 1 meter wide mouth. And in the weird world of molecular flow, the size of that opening is everything. Because a bigger opening means, well, it means a mind-boggling increase in speed. A large diffusion pump can pull molecules out of a chamber at a rate of 50,000 liters every single second. It's an almost unimaginable amount of nothing.
So why does this matter? Ultimately, the diffusion pump didn't just improve vacuum technology, it completely shattered the old mechanical limits. The ability to create huge, clean, empty spaces quickly and cheaply
Well, that became the invisible engine that powered the entire age of electronics. It enabled the mass production of everything from the first vacuum tubes to the microchips we use today.
See that silvery mirror coating on the inside? If you've ever seen an old radio tube, you know exactly what I'm talking about. So what if I told you that that little mirror was the key to a technology that helped win World War II? Yeah, seriously. So how on earth does that connect? Let's find out.
Okay, so the first huge problem with making a vacuum tube is, well, it's right there in the name, the vacuum. You have to create this almost perfect nothing inside the glass. But actually making that nothing and then making sure it stays a nothing, that was a gigantic engineering challenge.
You know, you'd think the biggest problem would be just pumping the air out, right? Nope. The real enemy was already hiding inside. The metals themselves, the nickel, the molybdenum, the tungsten filaments, they were basically contaminated, riddled with these tiny, microscopic pockets of gas. Stuff like nitrogen and hydrogen, just trapped deep inside the metal.
So what do? Well, the manufacturers pretty much have to go to war with these metals. It was this brutal three-step assault. First, you pump out all the easy stuff, the free-floating air. Then you bake the whole glass tube to get rid of any water vapor. But the final step, that was the crazy part. They would blast the metal guts with induction coils, heating them up until they were glowing white hot, literally boiling those trapped gases right out of the solid metal.
And when I say hot, I am not kidding. We are talking about absolutely staggering temperatures. For the tungsten filaments, they had to flash them at something like 2,300 degrees Celsius. To put that in perspective, that is nearly half as hot as the surface of the sun. All of that just to force out these stubborn little gas molecules. But here's the kicker. Even after all of that insane heating process, it still wasn't a perfect fix. Over time, as the tube was used, little bits of gas would still manage to sneak out of the metal. It would poison the vacuum, kill the tube's performance. Basically, it was a massive reliability nightmare. Brute force just wasn't cutting it.
So they needed something smarter, something more elegant. They needed like a chemical guardian that could stand watch inside the tube 24/7, protecting that precious vacuum. The answer wasn't going to be about more heat or more pumps. It was going to be about chemistry.
And that brings us to this brilliant little invention called the getter. So what is it? It's basically a little patch of a super reactive metal, think barium or zirconium, that they stick inside the tube. Its entire purpose in life is to be a chemical scavenger. It just sits there waiting to pounce on and trap any stray gas molecule that has the bad luck to wander by.
So remember that silver mirror we talked about? This is where it comes from. During the final step of making the tube, they'd zap that getter with an induction coil. It would instantly vaporize into a tiny cloud of metal. That cloud would grab onto any last bits of gas and then condense on the inside of the glass, creating that mirror. So it's not just for looks, it's a silent, tireless chemical vacuum pump working for the entire life of the tube. And they got really clever with this. There were basically two main flavors of these getters. You had the barium type, which acted like a chemical flytrap, creating this porous film where gas molecules would get stuck. But then you had the zirconium type, which was even crazier. It didn't just trap the gas on the surface, it absorbed it right into the metal itself. We're talking about absorbing 40 times its own volume in gas. I mean, that's just wild. Super ingenious chemistry at work.
Okay, so mastering the vacuum like this wasn't just about making better radios. It completely set the stage for the next huge technological leap. And this one was driven by the desperate urgency of World War II. The war was all about air power, and to win in the air, you needed a new kind of sight. You needed airborne radar. Now, early radar was amazing. I mean, Britain's chain home system was a game changer in the Battle of Britain. But there was a big problem. It used really long wavelengths, which meant it needed absolutely enormous antennas. We're talking towers over 100 meters tall. You can't exactly strap one of those to the wing of a Spitfire, right? The answer had to be microwaves. Their wavelengths are way shorter, so you can use small, compact antennas that would actually fit on a plane. The huge challenge, though, was generating enough power at those frequencies. But with the pressure of the war on, technological development went into overdrive, and in 1940, there was a massive breakthrough.
And that breakthrough was this thing, the resonant cavity magnetron. It was a totally different kind of vacuum tube. It basically used a super powerful magnet to whip electrons into a spinning vortex. And as this electron cloud spun past these little copper cavities, it created just a huge blast of microwave energy.
Look, the physics gets pretty hairy, but there's a really great analogy for it.
Think about blowing across the top of a soda bottle to make that humming sound. The magnetron is doing basically the same thing, just instead of your breath, it's using a spinning storm of electrons, and instead of a low hum, it's creating a deafening scream of microwave power.
And the amount of power we're talking about here is just mind-boggling. Not kilowatts, we're talking pulses of megawatts of power. It was a leap in technology that nobody thought was possible. And just like that, the magnetron became the heart of every Allied radar set. It completely changed the game. But as always in engineering, solving one huge problem creates another one. Now you have this incredible power source, but how do you tame it? How do you unleash this massive blast of energy and then, a split second later, listen for a tiny echo without completely frying your own equipment? And that brings us to the radar paradox. You have one antenna. It has to do two things. First, it has to scream out a megawatt pulse, a blinding flash of energy. Then, a microsecond later, it has to listen for a return echo that's barely a whisper. That massive transmit pulse would instantly vaporize the sensitive receiver. So they needed a switch, but not just any switch. They needed one that could work quite literally at the speed of light.
The solution, believe it or not, was yet another clever vacuum tube. This one was called the TR switch, for transmit-receive. And here's the genius part. Unlike all those other tubes that needed a perfect vacuum, this one was intentionally filled with a special low-pressure gas. And that gas was the whole secret.
Okay, so here's how it worked. When the magnetron fires its massive pulse, that wave of energy hits the TR tube. The gas inside instantly lights up, turning into a plasma, basically a conductive gas. For that tiny instant, the plasma acts like a solid metal wall. It completely blocks the path to the delicate receiver and reflects all that power out the antenna. And then, and this is the beautiful part, the very instant that pulse ends, the plasma just vanishes. It collapses back into a normal, invisible gas. Suddenly, the path to the receiver is wide open, totally clear, so that faint little echo coming back from the target can pass right through, safe and sound. It's a perfect switch, with zero moving parts, flipping on and off at the speed of light. Absolutely brilliant.
So when you put it all together, you see this amazing chain of invention, this incredible legacy, and it all happened inside a simple little glass tube. It's just a cascade of one brilliant idea after another.
It really was a chain reaction of genius, wasn't it? First, you solved the perfect vacuum problem with that clever chemical getter. That makes reliable tubes possible. Then, that reliability lets you build the incredibly powerful magnetron for airborne radar. But the magnetron's insane power creates a new problem, how to not deafen yourself, which is then solved by the speed of light TR switch. Every single solution created the next problem and the next breakthrough.
We're going to dive into two absolutely massive engineering headaches that were solved under the insane pressure of a world at war, and both of them hinged on taming the vacuum. So you've got these two totally different problems. On one side, you have this brutal challenge of speed and force. How do you make fragile electronics survive inside an exploding shell? And on the other, you've got this impossibly delicate, almost microscopic problem. How do you sift individual atoms in a factory the size of a city? Well, it turns out the answer to both was the void. Let's tackle that first problem. You gotta picture this. Before this invention, trying to hit a fast-moving airplane with an anti-aircraft gun was, well, it was basically a crapshoot. Gunners had to guess the altitude, guess the speed, and most of the shells just burst in empty sky. They needed something better. They needed a fuse that could actually think for itself. And this was the solution, the proximity fuse. I mean, think about it. It was a tiny, complete radar system stuffed into the tip of a shell. So instead of a simple timer, it would actually sense when it was getting close to an enemy plane, and then, and only then, boom. It was a total, absolute game changer. Okay, get ready for this number, because this is the heart of the problem. The tiny electronics packed inside that fuse had to survive being shot out of a cannon. We are talking about an acceleration of 22,000 times the force of gravity. That's just, it's an insane number. How could anything that delicate possibly survive that? And look, the folks working on this, they knew how nuts this was. The team at the top secret Section T were staring at a problem that everyone, and I mean everyone, thought was completely and utterly impossible to solve. So how in the world did they pull it off? Well, it was a whole string of brilliant, clever hacks. First, they shrunk down the vacuum tubes. You know, the fragile glass bulbs that were the brains of all electronics back then? Down to the size of a pencil eraser. Then, they suspended these little guys in plastic and encased the whole thing in a special shock-absorbing wax. Even the battery was pure genius. It actually used the violent spin of the shell itself to come to life in midair. So let's walk through how this thing actually worked. The second that shell leaves the cannon, bam, the G-forces kick the battery into life. The tiny vacuum tubes fire up and start sending out a radio signal. When that signal bounces off an enemy plane, the receiver inside the fuse picks it up, and a special little trigger tube detonates the shell at the absolute perfect moment. Just brilliant. Okay, so that's the story of conquering brute force. Now let's switch gears completely. Because while all that was happening, the Manhattan Project was wrestling with a problem of mind-boggling scale and delicacy: how to make the fuel for an atomic bomb. The challenge was separating two flavors of uranium. You have U-238, which is everywhere, and then you have the really rare fissile U-235. They're chemically identical, so the only difference is a tiny, tiny bit of weight. The method they landed on was called gaseous diffusion. Think of it like a giant microscopic sieve. You turn the uranium into a gas, push it at a barrier with billions of tiny holes, and the slightly lighter U-235 atoms sneak through just a fraction faster. And the gas they had to work with? Uranium hexafluoride. I mean, this stuff was a complete and total nightmare. It would literally eat through metal. If it touched even one molecule of water vapor, it would react violently. If the temperature wasn't absolutely perfect, it would turn back into a solid. The only way to handle it was to keep the whole system in a giant, flawless vacuum. And when we talk about scale, it's just hard to even wrap your head around. The K-25 plant they built in Tennessee was, at the time, the biggest building on the planet. This half-a-mile-long monster was basically one single, gigantic, perfectly sealed vacuum chamber with thousands of miles of pipes inside. Which brings us to the $500 million question. For this whole thing to work, that entire massive system had to be perfectly airtight. One microscopic leak could let in moisture, wreck the gas, clog up the works, and bring the whole thing to a grinding, catastrophic halt. So how on earth do you find a leak that small in a factory that big? Well, the hero of this story is a physicist named Alfred Neer, and his idea was brilliant. He took this super delicate, complicated lab instrument called a mass spectrometer, which is basically a machine that can identify atoms by their weight, and he figured out how to turn it into a tough, portable leak detector that could work on a factory floor. The process itself was just beautiful. A technician would hook up the mass spectrometer to a piece of the pipe system and pull a vacuum. Then, another tech would walk around the outside, spraying a fine mist of helium gas all over the pipes and welds. If there was a leak, even a pinprick, swoop, the helium gets sucked inside. The spectrometer, which was tuned to listen only for helium's unique atomic signature, would instantly let out this loud squeal, pinpointing the leak exactly. So you take a step back and look at these two stories, a tiny little fuse and this factory the size of a city. They seem like they're from different planets, right? But they're not. They both show science just staring down impossible engineering problems and winning. I mean, just look at how it breaks down. The proximity fuse team, they tamed G-forces with tough little vacuum tubes. And that kicked off the entire post-war electronics boom, everything from hearing aids to aerospace tech. And the K-25 team, they tamed the perfect vacuum on a massive scale. That not only gave us the fuel for the bomb, but it also created industrial techniques we still rely on today. And the sheer scale of these projects is just off the charts. We're talking more than 20 million of these smart fuses being cranked out, completely changing warfare in the air and at sea. Meanwhile, the K-25 plant cost $500 million back in 1945. That is just an insane amount of money to produce just a few pounds of material.
Today, we're going to talk about a machine born from the incredible pressures of war. I mean, this thing was a 30-ton giant that became the world's first general-purpose electronic digital computer. This is the story of ENIAC.
Now, to really get ENIAC, you have to start with the problem it was built to solve. We're talking about the height of World War II, and the stakes could not have been higher. The question facing the US Army was just massive. How do you solve a math problem that could literally decide the outcome of a battle?
And that brings us right to the heart of the issue. They were facing a huge, and I mean huge, wartime calculation crisis. The speed of warfare was just exploding, but the math?
The math was stuck in the past.
So here's the specific problem. The Army had all these new artillery pieces, and to aim them accurately, you need these things called firing tables. But these aren't simple calculations, not at all. We're talking incredibly complex equations that had to account for literally everything: projectile mass, wind speed, air density, even the temperature of the gunpowder.
And this right here shows you the massive disconnect. On one hand, you had your human computers, mostly brilliant female mathematicians, by the way, using these clunky, clattering mechanical calculators. The work was just grindingly slow and, of course, prone to human error. But on the other hand, what the war demanded was the complete opposite. A massive number of tables, needed super fast and with near-perfect accuracy. The old way just wasn't going to cut it.
So clearly, they needed a totally new approach. A real leap in thinking that would take calculation out of the physical world of gears and into the, well, the weightless, invisible realm of electrons.
And this was the revolutionary idea from a physicist named John Mauchly and an engineer, J. Presper Eckert. They basically proposed building a giant mathematical robot. The big idea? Instead of relying on slow, moving physical parts like gears and cogs, they were going to harness the almost instantaneous flow of electrons to do all the heavy lifting.
And the beating heart of this new machine? It was the humble vacuum tube. Yeah, the same kind of thing you'd find in an old radio. Eckert and Mauchly figured out how to repurpose it into a super high-speed switch. It could flip between on and off, a 1 or a 0, in just microseconds. This was the foundation for digital logic.
And you have to understand, this was a world-altering change. Mechanical parts have inertia, right? They take time to start and stop moving. We're talking milliseconds. Electrons, on the other hand, they have virtually no mass. You can start them and stop them almost instantly, measured in microseconds. This wasn't just a small improvement. It was a fundamental shift in the speed of thought itself.
Okay, so the theory was solid, but turning that electronic dream into a 30-ton reality, well, that was going to take an engineering effort on a scale nobody had ever seen before. First, just think about the sheer scale of this thing. ENIAC weighed 30 tons. It was an absolute monster of a machine.
It took up 1,500 square feet of floor space. That's about the size of a small house, just packed, wall to wall with computing hardware.
And inside this massive frame, an absolutely mind-boggling 17,468 vacuum tubes. That was the electronic heart of the machine, all of them constantly glowing with heat.
At all those tubes, they sucked down a colossal amount of power, 160 kilowatts. It generated so much heat that the room temperature could hit a blistering 120 degrees Fahrenheit. They needed two 20-horsepower industrial blowers just to keep the whole thing from literally melting down.
And this quote just captures the scale perfectly. Now, it might be a bit of an exaggeration, but the legend that the streetlights in Philadelphia would actually dim when they fired up ENIAC, well, that gives you a real visceral sense of the kind of power this machine was pulling from the grid.
So what did all that size and all that power actually get you? This. A calculation for a 60-second artillery trajectory, something that would take a human expert 20 hours with a desk calculator, ENIAC could knock out in just 30 seconds. That is 2,400 times faster, an absolutely world-changing leap in speed.
But all that amazing hardware was only half the story. I mean, the machine was a genius, sure, but it needed a whole different kind of genius to actually tell it what to do. And that's where we get to the story of its unsung human programmers.
It's really critical to understand this. ENIAC was not a computer like we think of one today. It had no keyboard, no screen, no operating system, and no software. Not a single line of code. To give it a new problem, you had to physically rebuild its circuits, every single time. And this absolutely monumental task fell to a team of 6 brilliant female mathematicians. First, they had to translate the complex math into physical circuit diagrams. Then came the grueling physical labor of plugging and unplugging thousands of heavy cables and meticulously setting over 6,000 rotary dials just to guide the flow of pulses through the machine. You know, a single programming change could take them 2 days.
Armed with only the machine's incredibly complex schematics, these women, whose work was tragically overlooked for decades, they effectively invented the entire discipline of computer programming, literally from scratch.
At the same time, the engineers were fighting a completely different battle, just keeping the thing running.
With almost 18,000 tubes, the odds of a single one failing were astronomically high. We're talking a 1 in 1.8 billion chance of failure every single second. So they came up with these extreme routines. They left it on 24/7 to avoid thermal shock. They ran parts below their max ratings. They even did nightly dim tube hunts, visually checking for failing parts before they broke.
So the success of both the incredible hardware and the brilliant human programming proved something massive. It proved that large-scale electronic computing wasn't just possible, it was practical. And in doing so, it really did usher in the dawn of the digital age.
ENIAC was, without a doubt, a monumental success, but it was also a monumental pain in the neck to program. Its biggest limitation, that whole exhausting process of physically rewiring it for every problem, well, that created this urgent need for a better way.
And you can draw a straight line from there to the device you're watching this on right now. Seriously, ENIAC's success in '46 directly led to this new idea called the stored program computer, where the instructions could be stored in memory right alongside the data. That single idea gave birth to commercial computers like UNIVAC and kicked off the entire hardware and software revolution that, defines our world today.
The atomic age kicked things off, sure, but the real pressure cooker was the space race. When the Soviet Union launched Sputnik 1 in October 1957, and then Sputnik 2 just a month later, that sent an absolute shockwave through the Western world. Suddenly, there was this massive mobilization of resources. If you wanted to build rockets and satellites, you had to test them in the airless conditions of space, but you had to do it while you were still on the ground.
And it wasn't just about space. Air, even tiny, microscopic amounts of it, was a huge problem. In advanced electronics, like the klystron tubes that generate powerful microwaves for radar and particle accelerators, any stray gas molecule could get zapped by a high-voltage beam, and that would cause a catastrophic failure. The air quite simply had to go, period.
But here was the big hurdle. The technology they had for creating vacuums, it just wasn't good enough. In fact, it was actively making the problem worse, leading to a full-blown contamination crisis at the microscopic level. So let me introduce you to the villain of our story. Backstreaming. You see, the old vacuum pumps worked by boiling oil, but this created a fatal flaw. A fine mist of oil vapor would actually creep backward into the supposedly clean chamber, coating everything with this microscopic film of gunk. For sensitive atomic research, this was a complete and total disaster.
So you see the problem, right? This huge purity gap. The old pumps left behind an oily mess. But the new era of science demanded a level of cleanliness so extreme they were talking about individual atoms. The old tech just couldn't do it. A totally new approach was needed.
And that brings us to our first hero, a major mechanical breakthrough called the turbomolecular pump. Now, this wasn't just an improvement, it was a complete reinvention of how to create a vacuum.
To really get a sense of this breakthrough, just listen to how its inventor, Dr. Willy Becker, described it. He basically said, forget old oily pumps and instead, picture a jet engine. That gives you a feel for the incredible power and precision we're talking about. This was a machine built for speed.
So how does this jet engine work? Well, it's brilliantly simple in concept. A gas molecule just wanders in and wham! It gets hit by a blade spinning at an incredible speed. That collision is like a baseball bat hitting a ball. It transfers kinetic energy, knocking the molecule down toward the next stage and the next, until it's forced right out the exhaust.
And when I say incredible speed, I really mean it. These rotors could spin up to 90,000 revolutions per minute. 90,000! That's a level of mechanical engineering that was just astounding for the 1950s. It's this sheer velocity that makes the whole process possible.
The result was a total game changer. By using pure mechanics instead of oil, the backstreaming problem was solved. Gone. This clean, reliable vacuum became the new standard, and it paved the way for decades of research.
But moving gas out was only one solution. A second, and maybe even more ingenious approach was being developed at the same time. A pump that didn't remove gas, but instead trapped it forever.
And this brilliantly illustrates the two different philosophies here. The turbo pump is like a bouncer, physically throwing molecules out of the club. The ion pump, on the other hand, is like a molecular prison, trapping them so they can never cause trouble again.
This molecular prison was invented in 1957 at Varian Associates. And get this, the company was founded by the very people who invented the klystron tubes that needed these vacuums in the first place. But the seed of the idea came from an observation made 20 years earlier, which just goes to show how scientific progress often builds on forgotten discoveries.
Now this is just genius. The ion pump uses a multi-pronged attack.
Active gases like oxygen are forced to chemically bond with a constantly refreshed layer of superreactive titanium. Lighter gases like hydrogen are smashed so hard into the metal walls that they get permanently stuck inside. And those inert gases that don't react, well, they get physically buried under layers of sputtered titanium atoms. There's literally no escape.
And the advantage of this approach is incredible. With zero moving parts, it's completely silent and vibration-free, which is absolutely critical for things like electron microscopes. And because it just traps atoms, it can run continuously for years, maintaining a perfectly clean, ultra-high vacuum.
So what happened after these two revolutionary inventions? How did this new power to create nothing change everything? The legacy is just staggering. I mean, particle accelerators, electron microscopes, the entire semiconductor industry that builds our computer chips, and of course space simulation, none of it would be possible without the pristine, ultra-high vacuums created by these pumps. So much of our modern world is built on a foundation of almost perfect nothingness. It's wild to think about.
Well, that brings us to the hero of our story, the cryopump.
A cryopump is just an amazing piece of engineering. It doesn't work like the vacuum cleaner you have at home by sucking air out. Nope. Instead, it works by making its internal surfaces so unbelievably cold, we're talking close to absolute zero, that any gas molecule that bumps into them instantly loses all its energy and freezes solid. It just stops dead in its tracks.
And this whole freezing process happens in two stages. The first stage is kind of like the gatekeeper. It cools down to about 80 Kelvin, which is cold enough to freeze out the easy stuff, like any water vapor floating around. But then the inner second stage goes into a true deep freeze. It drops all the way below 20 Kelvin, and that's cold enough to solidify pretty much everything else. Nitrogen, oxygen, argon, you name it.
But, there are always a few troublemakers. A few super-light gases like hydrogen, helium, and neon. They just refuse to freeze, even at those insane temperatures. So the solution here is just brilliant. The coldest part of the pump is lined with this stuff called activated charcoal. It's super porous, and it basically acts like a molecular sponge, physically trapping these last few rogue molecules that nobody else can catch.
But, like a lot of amazing tech, this is kind of a double-edged sword. On the one hand, the huge pro is that cryopumps are incredibly fast and they create these unbelievably pure vacuums. But the con? Well, because it's a capture pump, it's just freezing and trapping the gas, it eventually gets full. So every so often, you have to take it offline, warm it up, and let it release everything it's captured. That process is called regeneration.
And that really gets to the core of what we're talking about today. It's a paradox that basically runs our entire modern world. The more insanely complex our technology gets, the more it depends on absolutely nothing. It sounds completely backwards, I know, but it's a fundamental rule of the digital age.
So on one side, you've got the mind-boggling complexity of a modern microchip. It's like a tiny, sprawling city of circuits. And on the other, you have the pure, simple emptiness of a perfect vacuum. But here's the crazy part. In the world of high-tech manufacturing, these two things aren't opposites at all. You literally cannot create one without the other.
So, let's get right into the heart of this paradox. To really get your head around it, you first have to appreciate the just insane scale we're dealing with when we talk about a modern semiconductor.
This right here really puts it into perspective. Inside a single chip, something no bigger than your thumbnail, there are roughly 60 miles of microscopic copper wiring. Think about that. That's like unwinding a wire from downtown Manhattan all the way to New Haven, Connecticut, and then squishing it all into something the size of a postage stamp.
And get this, crammed all along those 60 miles of wiring, you're looking at tens of billions of tiny, nanoscale switches. We call them transistors. These little things are the fundamental building blocks of all modern electronics. And the fact that we can pack so many of them in is what makes our devices so ridiculously powerful.
So you can probably see where this is going. When you pack things that tightly together, you create an extreme vulnerability. To build something so incredibly small, you need an environment that is impossibly clean. Basically, you need an environment made of pure nothingness.
I mean, seriously, just think about it for a second. We're not just building small things anymore. We are literally assembling devices where the components are measured in atoms. So what do you think happens when just one unwanted particle shows up to the party?
This is where the scale just completely messes with our intuition. At that tiny, tiny level, a single stray particle or a water molecule isn't just a speck of dust. No, it's a massive boulder crashing right into your construction site.
It causes a catastrophic defect that can wipe out an entire section of the chip, rendering it useless.
And that's really the bottom line here. As we keep pushing the boundaries of physics, making these transistors smaller and smaller, our margin for error has just completely disappeared. It's gone. You need absolute perfect purity. And there's only one way to get that. You have to completely seal it off from our planet's atmosphere. So how in the world do they actually do it? Well, this brings us right to the manufacturing process, which is kind of like a modern-day alchemy, the alchemy of thin films. And this is where that perfect vacuum we've been talking about goes from being important to being absolutely non-negotiable. At the core of all this is a technique called atomic layer deposition, or ALD for short. And this is truly the pinnacle of precision manufacturing. I mean, imagine, you're not painting with a brush, but you're placing individual atoms down one by one to build up a perfectly even layer across the surface. That's ALD. The way ALD works is this really precise four-step dance that repeats thousands upon thousands of times. First, you pulse one gas into the chamber. Then, and this is the most important part, you have to completely purge the chamber, get every single last molecule of that gas out. Only then do you introduce a second chemical. And then, you guessed it, another complete purge.
Now, those purge steps, they put an insane amount of stress on the equipment. To pull every molecule out of that chamber, and to do it that fast, you need vacuum pumps with just monstrous power. We're talking about the ability to move 4,500 cubic meters of gas an hour just to create that perfect empty moment between atomic layers.
You see, to make our computer chips smaller and faster and more powerful, engineers first had to figure out a way to get around the physical limits of light itself.
For decades, the industry used a method called deep ultraviolet, or DUV, lithography, and it was fine for a while. But with a wavelength of 193 nanometers, it's like trying to paint a microscopic circuit with a really thick paintbrush. It just physically could not draw the super fine lines needed for the transistors we have today. The new method, EUV, uses light with a wavelength that's over 14 times smaller. But, and this is the key, it requires a totally different environment, an ultra-high vacuum. So the whole industry had to make this huge shift to a new kind of light, extreme ultraviolet, or EUV. It's sharp enough to draw those impossibly small circuits, but it also comes with one massive, staggering complication.
Now that wavelength you see there, 13.5 nanometers, that is super interesting. It's not just some random number. Turns out it's the perfect frequency of light for etching these incredibly intricate patterns onto silicon wafers. It's what lets us pack billions and billions more transistors into the same tiny space. And here's the paradox. The very thing that makes EUV light so great, all that energy, also makes it a nightmare to work with. It's just so reactive that it gets completely absorbed by anything it touches. That includes the air in the room. So you have no choice but to put this whole machine, which is about the size of a city bus, inside a massive, perfect vacuum. Okay, so that leads to the next obvious challenge, right? If the whole machine is basically a giant sealed metal box, how in the world do you even create this special kind of light on the inside? Well, the answer is with extraordinary violence. What you do is fire one of the world's most powerful CO2 lasers at a tiny, microscopic droplet of molten tin that's falling through the vacuum chamber. The laser blast instantly vaporizes the tin into a superheated plasma, and that plasma glows, emitting the exact EUV light that you need. And get this isn't something that happens once in a while. This process, vaporizing a tiny droplet of tin, happens 50,000 times every single second. It is a constant barrage of tiny, perfectly controlled explosions going off inside this machine. But as you can imagine, 50,000 tiny explosions every second has a pretty disastrous side effect. It creates what's essentially a cloud of high-energy tin shrapnel. These little ions and particles go flying off in every direction, threatening to tear apart the multi-million-dollar machine from the inside. And here's where it gets really hairy. That debris flies straight at the most important, most expensive part of the whole system, the huge collector mirror. If even a microscopic layer of tin builds up on that mirror, it can't reflect the EUV light, and the entire billion-dollar operation just grinds to a halt. So the very process of creating the light is also destroying the tool you need to collect it. This massive problem led to one of the most clever, most counterintuitive engineering solutions you can possibly imagine.
I know, it sounds totally nuts, right? To solve a contamination problem that's happening inside one of the most pristine vacuums on Earth,
engineers decided to deliberately pump massive amounts of hydrogen gas right into it, it just sounds wrong.
But this paradoxical fix is actually brilliant because it works in two ways. First, the hydrogen molecules act like a physical shield, literally bumping into the tin particles and slowing them down. But even more importantly, the process creates these highly reactive hydrogen radicals, which then chemically attack any tin that does manage to stick to the mirror. It turns the tin into a harmless gas that can then just be safely pumped away.
But this whole incredible dance of light and plasma and gas, it would all be completely impossible without a foundational invention from decades ago. An invention that solved what you might call the original sin of vacuum technology.
You see, way back in the 70s, the pumps used to create a vacuum used oil. But here's the problem. Even a single molecule of that oil getting back into the chamber could destroy an entire batch of incredibly valuable computer chips. The whole problem was finally solved in 1980 when an engineer named Henry Wycliffe invented the first practical oil-free dry pump, and it completely changed the game.
This one invention, this dry pump, it was the key that unlocked everything. It's what allowed the entire industry to move to the kind of pristine, continuous, super reliable vacuum environments that are absolutely essential for making the complex chips we all depend on today.
So, all of this layered, mind-bending complexity brings us to the staggering consequence of it all, the absolutely astronomical cost.
A single one of these EUV systems is, and I'm not exaggerating here, among the most complex machines ever put together by human beings. We're talking over 100,000 highly specialized, custom-made components.
And you can bet that the price tag reflects that complexity. The cost for just one of these machines isn't $1 million, it's not 10 million, it's somewhere between $300 and $400 million for one machine.
And because a modern chip factory, what they call a fab, needs dozens of these EUV tools running 24/7, plus hundreds of other vacuum chambers, the cost to build just one new facility easily blows past $10 billion. A massive chunk of that cost is just building and maintaining the perfect void.
So at the end of the day, in this multi-billion-dollar void, reliability is absolutely everything. Any failure, any tiny bit of contamination means incredibly expensive downtime, and that can cost a chip maker millions of dollars a day.
The Semiconductor Gigafab. This is where the magic happens, where the world's computer chips are actually born. You have to understand, a single one of these places isn't just a factory. It's practically a city built for emptiness. We're talking thousands of vacuum pumps, all humming in perfect harmony, linked by miles of piping that costs billions of dollars. And with our tech appetite growing, the demand for this stuff is just exploding. Even when the chips are finally done, they get shipped around the globe in, you guessed it, vacuum-sealed trays. The whole supply chain is built around a perfect void. But inside these unbelievably clean environments, there's a war going on. Engineers are fighting a constant battle against an enemy so tiny it's almost invisible, but so powerful it can wreck billions of dollars in product. That enemy? Microscopic dust. And here is where things get really wild. It's a maddening paradox. The very tool you use to create that pristine, clean environment, the vacuum pump, can actually be the thing that creates the contamination you're trying so hard to avoid. How is that even possible? Well, it all comes down to a process called turbulent nucleation. See, if you suck the air out of a chamber too fast, the pressure drops like a rock, and that makes things get cold fast. Any tiny bit of moisture left in there instantly condenses around little particles, and poof, you've just created a cloud of killer dust right above your priceless silicon wafer. So you can see the two approaches right here. On one side, you have aggressive pumping. It's just chaos. It creates turbulence, kicks up all these particles, and basically guarantees contamination. But on the other side, you have the solution, staged pumping. It's all about gentle, controlled pressure drops that keep everything calm and protect that perfect surface. So the process they use is like a carefully choreographed dance. You start slow with a really gentle pressure drop, just to get most of the air and moisture out of the way. And only then, when the coast is clear and there's no risk of making that dust cloud, do they fire up the big guns, the high-speed turbo pumps, to pull that deep, perfect vacuum. And you gotta love this part. Sometimes the most ingenious solutions are also the simplest. Get this. Inside a vacuum, there's no air for dust to float around in. So if a particle does appear, it just falls straight down thanks to gravity.
So what do the engineers do? They simply flip the silicon wafers face down. It's brilliant. They use gravity to make the wafers protect themselves, a totally low-tech trick in the most high-tech environment imaginable. Okay, so we've established how critical this is. But creating all of this emptiness on a massive global scale, well, it comes with a pretty staggering price tag. And I'm not just talking about money, I'm talking about energy. Check this out. In your average chip fab, a full 1/4 of the entire electricity bill goes to just one thing: running the vacuum pumps, 24 hours a day, 7 days a week. That is an insane amount of power just to maintain nothingness. And when you zoom out and look at the whole industry worldwide, the numbers are just astronomical. We're talking 160 terawatt hours of electricity every single year. That's a huge strain on power grids all around the world, all in the service of the void. And this is leading to a major problem. If the industry keeps growing like it is without changing anything, its carbon emissions could jump by 8 times by 2030. That's a trajectory that is just not sustainable and clashes head-on with climate goals.
But the good news is the industry knows this, and it's pivoting hard towards what they call green vacuum technology. So where the old pumps just ran full blast all the time, these new smart pumps can cut energy use by up to 60%. They have idle mode so they can power down when they're not needed, and they're all connected with AI and sensors to optimize power use across the entire factory. It saves a ton of money and a ton of energy.
Now, if you think a chip fab is an extreme environment, you haven't seen anything yet. For our final act, we're going to the absolute frontier of emptiness. We're going to CERN, home of the Large Hadron Collider, where they are literally engineering a vacuum to try and recreate the conditions of the Big Bang. The scale of this thing it's just hard to wrap your head around. The vacuum system at the LHC isn't a little chamber. It is a network of pipes that stretches for 104 kilometers under the border of France and Switzerland. And to pull this off, huge sections of the machine are chilled to 1.9 Kelvin. That is just a tiny fraction of a degree above absolute zero, the coldest temperature that can possibly exist. It makes the LHC one of the coldest places in the entire universe, colder even than empty space. And what do you get for all that effort? You get a vacuum so deep, the pressure inside is down to 10 to the minus 12 millibars. That is an almost impossibly perfect void. It has to be, so that the protons they're smashing together don't accidentally hit a single straight air molecule on their trip around the ring.
You know, a quote from one of the sources we looked at just says it all. The scientists at CERN have created an artificial void that is as highly rarefied as the desolate surface of the moon. They built a piece of the moon right here on Earth. Just incredible. So how in the world do they pull this off? Well, it's a two-part strategy. In those super long, curved sections, they use the extreme cold itself. The pipe walls get so cold, they act like a giant vacuum pump, freezing any molecule that touches them solid. That's called cryosorption. But in the straight sections that are at room temperature, they use something else, a special chemical coating called a getter that basically acts like molecular flypaper, trapping gas, along with powerful ion pumps. Two totally different challenges, two incredibly clever solutions. So as we've seen, this whole quest for emptiness is an amazing journey. It takes us from the microscopic perfection needed to build a single chip to the massive energy bill we all pay for our digital world, all the way to the most extreme voids humanity has ever created in our search for cosmic secrets.
How do you actually hear two black holes colliding a billion light years away? I mean, think about that. They send out these tiny, tiny ripples in space-time itself. How in the world are you supposed to catch something that faint from that far away?
Well, it's because the measurement you're trying to make it's almost impossible to even wrap your head around. We're talking about 10 to the minus 19 meters. That's the size of the wobble they're hunting for. To put that in perspective, that is 10,000 times smaller than the nucleus of a single atom. It just shouldn't be possible to measure that. At all.
So how do they do it? The answer is as wild as the problem itself. The key to that impossible precision is to build one of the emptiest places in the known universe, a void more perfect, more empty than deep space itself, but right here on our planet.
Okay, so our first big example is the Laser Interferometer Gravitational-Wave Observatory. You've probably heard of it, LIGO. Its entire job is to listen for those tiny cosmic whispers. And to do that, it needs a vacuum of absolutely epic proportions.
So when we say vacuum, we're not talking about your vacuum cleaner at home, not even close. We're talking about something called an ultra-high vacuum, or UHV. This is a state so empty, it's about 1/1,000,000th of the normal atmosphere we're breathing right now. For every trillion molecules out here, there's only one left in there. It's basically the absolute frontier of emptiness.
And at LIGO, the whole challenge is just the sheer scale of it. See, to catch those gravity waves, they shoot a laser back and forth between mirrors that are 4 kilometers apart. The problem? If that laser beam hits even one stray gas molecule, poof, the whole measurement is ruined. So what do? They build these 2 absolutely gigantic steel tubes, 4 kilometers long, creating one of the biggest vacuum systems on the planet.
And get this is the crazy part. The second you pump all the air out of those tubes, you've got the entire weight of Earth's atmosphere trying to crush them flat. We're talking about 150 million kilograms of force. That's just immense. It's the only reason they have those big, heavy rings on the outside, to literally stop the whole thing from imploding on itself. So, okay, how do you even begin to create a void like that? Well, it is an absolute ordeal. For starters, you have these massive pumps running nonstop for 40 days. 40 days! And that just gets rid of most of the air. But that's not nearly good enough. The real work comes next, a giant bakeout. They heat up the entire 8 kilometers of steel tubing for another 30 straight days, trying to force out every last molecule hiding in the metal.
All right, so that's LIGO's long, skinny vacuum. Now let's switch gears to a totally different kind of emptiness. We're talking about NASA. They don't need a long tube. They need to test entire spacecraft. They need a giant, cavernous chamber that can perfectly mimic the cold, empty void of space.
And the logic here is pretty simple, right? But the engineering is just mind-blowing. I mean, before you launch a billion-dollar piece of hardware into space, you better be darn sure it can handle it. It has to survive the brutal cold, the intense heat, and of course the total lack of air. So you basically have to build a little chunk of outer space right here on Earth. And this really shows you the 2 different paths to creating nothingness. On one hand, you've got LIGO, which needs that long, narrow void for its lasers. But then you have NASA's Space Power Facility, which is the world's largest vacuum chamber. It needs this huge, cavernous space, more than double the volume of LIGO, just to fit a whole spacecraft inside. And look at the materials. LIGO is all stainless steel. But NASA's chamber is so huge, the aluminum walls need a giant concrete building wrapped around them, just to stop the atmosphere from crushing it.
And to empty out a room that big, you need some serious power. To get it down to a vacuum in less than 8 hours, this facility has pumps that can suck out 500,000 liters of air every single second. That's just an insane amount of pumping power.
Okay, so you're probably thinking, with pumps like that, this must be easy. But this is where the story takes a fascinating turn. The biggest enemy in creating a perfect vacuum isn't the air you're pumping out. Nope. The real enemy is the walls of the chamber fighting back against you.
I love this quote because it nails the problem perfectly. The steel itself, the very material of the chamber, acts like a microscopic sponge. It might look and feel solid to us, but on an atomic level, it's packed with trapped gases.
And there's a name for this. It's called outgassing. The moment you start pumping the air out, the metal walls themselves start to slowly bleed these trapped molecules right back into your perfect vacuum. And when you're aiming for an ultra-high vacuum, this isn't some tiny little leak. It becomes your #1 enemy. And it turns out there are 2 main bad guys in this story. First, you've got water vapor. It just stubbornly clings to every metal surface with these strong hydrogen bonds. But the real villain? It's elemental hydrogen. This stuff got baked right into the atomic structure of the steel when it was manufactured. It's not on the metal, it's in the metal.
And this is why choosing the right material is everything. You can see it right here. If you tried to build one of these chambers out of regular old mild steel, forget it. It would outgas like crazy. Aluminum is a step up, but the real champion is 304L stainless steel. Its atomic structure is just so much denser, making it way less of a sponge. Getting this choice right is the very first and maybe the most important battle you have to win. But even with the absolute best steel money can buy, to get to the deepest, most extreme levels of vacuum, you've got to go even further. You have to literally wage war on the atoms trapped deep inside the metal itself. Remember that big bakeout they did at LIGO? That's a fantastic start. But for the really, really extreme vacuums, it's just not going to cut it. To truly win the war against outgassing, you have to do something radical. You have to reforge the steel.
And this is the final boss move. It's called vacuum firing. It's kind of crazy. You take your steel parts before you even build the chamber, and you stick them inside another vacuum chamber. Then you crank the heat up to a scorching 950 degrees Celsius and just hold it there for 24 hours. At that temperature, the actual atomic structure of the metal expands and it violently kicks out all that trapped hydrogen, for good.
And the result? It's just incredible. Steel that's been treated this way outgasses 100 times less than even standard stainless steel. That's not just a small improvement. That's the difference between a good vacuum and a vacuum that is right on the bleeding edge of what's physically possible.
And yet, after all of that, all this heroic engineering, the giant pumps, the month-long bakeouts, the atomic reforging, there's still a tiny, microscopic stream of atoms that just keeps trickling out from the walls, forever. A truly 100% perfect vacuum is impossible. It's something we can get closer and closer to, but can never actually reach.
All right, so to really get our heads around this, we have to start with a pretty wild claim. Modern physics has shown us that a true perfect void, like absolute total nothingness, is just not possible. The universe actually forbids it. That's right, it's a fundamental mathematical impossibility. So even if you could make a perfect box, cool it down to absolute zero, and suck every single particle out, it still wouldn't be empty. According to the strange rules of quantum mechanics, what we think of as a vacuum is actually a seething, energetic sea of potential. So why? Why can't a true vacuum exist? Well, the answer comes from the quantum world, and this isn't just some philosophical hand-waving. It's a direct result of the fundamental laws that govern our universe at the smallest scales. It all kicks off with this guy, the Heisenberg uncertainty principle. Now, you've probably heard of it. It basically says you can't know certain things with perfect precision at the same time. Well, that applies to energy too. If the energy in a vacuum was perfectly exactly zero, you'd know its value and its rate of change perfectly. And that's a big no-no. The universe just doesn't allow it. And because of that uncertainty, here's the kicker. The vacuum always has to have this baseline minimum amount of jiggling, fluctuating energy. We call it zero-point energy. It's the energy that's left over even at absolute zero, the coldest temperature theoretically possible. So what does this energy look like? Well, imagine a chaotic, boiling sea of what physicists call virtual particles. These are these little pairs of matter and antimatter that literally pop into existence from the void, have a fleeting moment, and then poof, they annihilate each other. The empty space all around you, right now, is fizzing with this unbelievable activity. Okay, I know what you're thinking. This sounds like something straight out of science fiction. Virtual particles, a boiling sea of nothing. But here's the thing, it's not theoretical. These quantum fluctuations have real, measurable effects. We have tangible proof that the void can push back. And that proof came back in 1948 from a Dutch physicist named Hendrik Casimir. He made this absolutely mind-blowing prediction. He figured if this quantum sea is real, then the void itself should be able to physically push things around. This idea, which we now call the Casimir effect, was the moment everything changed. So here's how it works. It's actually pretty simple. Imagine you take two perfectly flat, uncharged metal plates and you stick them in a vacuum, but you put them incredibly close together. Now, all those virtual particles, they act like waves. Outside the plates, you can have waves of all shapes and sizes, but in that tiny little gap between the plates, only very specific tiny wavelengths can fit. That means you've got more quantum waves pushing on the outside of the plates than on the inside. And the result? A net pressure that literally squeezes the plates together. And check this out. The scale of this force is just wild. When the plates are 1 micrometer apart, that's super tiny, the force is really small, about the weight of a single water droplet. But this force gets incredibly strong as they get closer. Squeeze those plates down to just 10 nanometers apart, and the pressure from the void, from nothing, becomes equal to 1 full Earth atmosphere. That is the insane power of empty space. And this is where our story comes full circle, because as our technology gets smaller and smaller, down to the nanoscale, that weird quantum fizzing of the vacuum, that Casimir effect we talked about, it stops being a scientific curiosity. It becomes a very real-world engineering headache. See, for engineers trying to design microscopic machines, things like nanobots, the vacuum isn't an empty stage anymore. It becomes this active and, get this, sticky medium. That little push from the void, the Casimir effect, is now strong enough to physically jam tiny moving parts together, clamping them shut. Literally, nothingness is getting in the way. So, okay, a perfect void might be impossible. But our pursuit of it, our attempt to create emptier and emptier spaces, well, that has been one of the single biggest drivers of technology in all of human history. It has completely reshaped our world. And you can see this whole story unfold right here. It all started with guys like Thomas Edison using these clunky early pumps to suck the air out of light bulbs so the filament wouldn't burn up. Then we got industrial pumps. Then it became absolutely critical in World War II for developing radar. And from there, well, it kickstarted the entire digital age. Just think about that. ENIAC, the very first general-purpose electronic computer, needed over 18,000 these fragile glass vacuum tubes to work. Our entire digital revolution was literally born inside a near void. And if you think that's just ancient history, think again. Our reliance on the void hasn't gone away. It's actually gotten way, way deeper. Today's most cutting-edge technologies are completely dependent on our ability to create and control, well, emptiness. I mean, it is no exaggeration to say that creating these ultra-high vacuum environments is the absolute bedrock of the modern world. From the processor in your phone to the biggest scientific experiments on Earth, it all happens inside a carefully engineered void. This stuff is everywhere. You can't manufacture the advanced semiconductors that power our entire world without a pristine vacuum. You can't smash particles together at the Large Hadron Collider. You can't even detect the faint ripples of gravity from colliding black holes without the massive vacuum chambers at LIGO. It's essential. And this quote just sums it all up perfectly, doesn't it? We set out trying to achieve the impossible, a perfect void. And in that relentless chase, we completely transformed our idea of nothing into the essential foundation of pretty much everything we build and everything we discover. So, the next time you look at what you think is just empty space, I want you to remember what's really going on in there. It's not an absence, it's not a void. It's a vibrant, buzzing cosmos, just brimming with the potential for particles, for forces, for infinite possibility. And that kind of leaves us with one final big question. If our most basic concept of nothing turned out to be so fantastically complex and so full of energy, what other fundamental things about our reality are we getting totally wrong? What else is hiding there, right in plain sight?